in the next section, I want to show you the standard model for computers that we use in algorithms these days. That's the random access machine. And this is, I saved this for the last part because it's a bit more intricate. And it has a little twist to it that we'll come to. And to motivate that, I'd like to ask you this question without saying too much. I've had 114 people vote on the attendance code earlier. It looks like you're more than 114. Not in age. Let's wait until we have 100 people voted, and then '98. All right. Ah, one more. Good. There's the results that people voted. And let me briefly discuss this a bit. There are really different answers that all make sense, depending on some assumptions that you make. So it could be that it takes constant time to add two numbers. So taking the concrete model I'll show you in a moment aside, on your computers that you have with you, it takes constant time if the numbers have at most 64 bits. Then it's quite guaranteed. Well, almost all computers these days have 64-bit architectures. So it fits in one word, and then there's one machine instruction that adds two numbers, bam, done. And it can do, I don't know, a few billion per second of these, right? Constant for us just means it doesn't depend on the input size. Now that's a little cheating, because if the numbers are big, it does take more time. And so the algorithmically more sensible answer is C. If the numbers keep growing, then it will be time proportional to the length of the numbers in bits. So I would say this is more correct, right? But if you write a program that always just uses numbers with at most 64 bits, the first answer is what you'll see. And OK, the last is of course correct, but we'll try to fix that. Maybe a quick comment. Why is it proportional to D? Well, you do the primary school method. You start with the last digit. You add those two digits up. There may be a carry digit, so you have 3 digits in the next step, but that's all. So you add these 3. Then you get the next digit. So in each step, you get 1 digit of the result produced. And you have D digits in total to process. Maybe it's D plus 1 in the end. But that should be it. All right. So the machine model is really important because it determines how algorithms look like It tells you what algorithms are possible and in what kind of language they are expressed. And it also defines usually what the cost of an execution is. And because it defines all these things, there's a few trade-offs that are tricky in general to get right. It should be detailed and powerful enough to reflect what current machines can do. For example, what I just said, if you have numbers with at most 64 bits, it's very fast to add them. Whereas if you have much longer numbers, it takes more time. Somehow the model should reflect that. It should also be abstract enough to not change every year. Otherwise, gone our eternal truths. But then also, we would like it to be simple enough to analyze it mathematically. So this first point and the last point are in clear opposition. So sometimes you may need a compromise and can't get all three. Here's the solution that algorithms research has essentially settled on. It's a bit of a mouthful, but don't get intimidated. It's just trying to define all that a computer can do in one slide, and so it has to go through a few different things. There's a book which is listed on the module page. So little digression, little aside. You know the module has a module website, which is linked on Canvas, but is living outside of Canvas on my personal website. And the module page has subpages for all the units. And unit 1 has the slides from today. We'll have the videos from today after some point. And also has a list of further reading and sources at the bottom. And there you'll find a link to this book. It's in the library in some form. Most books you can borrow from the library in electronic form, which is probably most convenient, but they also have some print copies. So the definition here is in much more detail described in this book, but I'll try to give you the short version. Our computers, the random access machines at least, have one big array of memory. It's essentially unlimited. You can use as much as you need. I'll comment on that in a second, why that sounds a bit weird, right? But why that might be okay. That's memory where you can store data. But to work with the data, you have to copy it to registers. And there you have a fixed number. And that number is not usually very important, so I'm generous. I allow you to tell me how many you want, but it should be somewhat reasonable, maybe a few hundred at most. Definitely independent of the input size. So you have to write a program that fixes the number of registers without knowing how big the input is that you work on. The memory cells themselves, they can each contain a number, and that number is an integer with W bits. And that's where things get a bit tricky in a way. We have this second parameter, W, that is part of the machine model. So you have to tell how large that is, and most current computers have essentially 64. Not too long ago, it was 32. If you're strict, then many of the computers actually have more than 64 because they have these SIMD instructions, single instruction, multiple data, where you can work on longer words, up to 265 at least, maybe some graphic cards even more. And they split this. It's treated as a vector where you can do vector-wise operations. So in a way, even 64 is playing it safe. But to come back to the formal model, each memory cell contains a number with W bits. So that's an integer between 0 and 2 to the W minus 1. And now the clue is that this word size is allowed to depend on the input size. That's a really weird concept. The machine grows with the input. And a typical assumption is that by and large, W is logarithmic in the input size. A quick motivation for why that roughly is if you write down the input in an array, you want to at least have a way to say, I want the ith bit in the input. And that number I should fit in one word, because that's mostly possible in computers. The second reason is you usually want to be able to use addresses to memory in operations. For example, you can add up 2 addresses in computer memory. And so to be able to do that, they should fit in 1 word. So this is a somewhat natural assumption, but maybe it looks really weird if you see it the first time. These 2 things, that the input is essentially unbounded and that the word size grows with the input, might look really strange. But if you look back historically, if you don't treat this as a model for 1 laptop on your desk, but for all of the computers over the history of computers, it makes a little more sense. The word size has kept growing over time. It started with single-digit number of bits, and then quickly went to 32, and now we're at 64, and even going beyond that with these SIMD instructions. And at the same time, the data that the computers worked on was also growing, and roughly in that relation, exponential growth. So don't treat it as a weirdness of the model that it seems to grow with the input. Imagine rather, if you want a bigger input to be solved, you have to build the machine up. You have to add more memory, and you have to increase the word size accordingly. Basically, any other way to define the model gives you other paradoxes for the theory that are not nice. All right, so I talked a lot about what the memory is like, how big it is, and how many bits you have in each memory cell. I will briefly talk about the instructions of the computer, but that's the slightly less important part. You have more leeway on this. But to be concrete, our computers here, the random access machines, can do basically 3 different things. One is they can load and store memory from data from memory. So you can get what's in a certain cell in memory and store it in a register. And the address is given by another register. So you can use indirect addressing. And you can do that for reading and writing. Then you can do all sorts of standard arithmetic on registers. So you can add 2 numbers, subtract, multiply, integer division, and integer modulo. And you can also do the C-style bitwise operations. I called them C-style because C popularized them back then, but most programming languages have operators for that. The same operators are used in Java and C# and so on. And Python has some way to express them as well. So you can, for example, take 2 numbers and do the bitwise AND. Treat the numbers as binary strings and do the AND of each digit, and a few other related ones. These won't be so relevant for this module, but I wanted to list them to be complete. And the third thing you can do is jumps and conditional jumps in your program. That's to do logic in the program. So you can say jump back to line so-and-so, and you can say only do that jump if a register is 0 or something like that. So here again, you can compare 2 registers. We don't necessarily care about the fine detail here. That's the 3 types of things you can do. That's very similar to most. If you've done some undergrad in computer science, you will probably have done some assembly language, where you've built some, you've at least conceptually built a processor. And that's the kind of operations they support. So this is very close to the silicon that we actually use, but it's a bit abstracted from some details. The cost in the model, how long does a program take? In this model is assuming it's exactly the number of executed instructions. So again, for the experts, I'll point out that accessing memory here is assumed to take these kind of instructions. They take constant time, and they are as fast as doing arithmetic. That's often not true in reality, but as a first-order approximation, that's what we assume here. Any questions on that model for now? I know it's been a lot of info, maybe. Because it's very, very low level. I said it's close to silicon style, what actual processors have as operations. It's very inconvenient to write any complicated algorithm in that level of detail. So we'll usually allow ourselves to do something that's closer to Python code. And you either have seen a compiler lecture or you have to take my word for it that it's a solved problem how to translate from this more high-level description, if it's precise like Python, down to what I've just shown you. That's an automated process. That's what compilers can do. And they're usually even smart about it to make some optimizations along the way. So we'll ignore that step. For us, algorithms will live at a slightly higher level. But we'll know that if needed, we can go back to this slightly lower detailed level to measure the performance. Because we allow ourselves to work with this more abstract pseudocode, what we'll usually do is count dominant operations. So we don't count all instructions in the RAM program, because that would need us to write down exactly the program that we want to analyze. There's a famous theoretical computer scientist, Donald Knuth, who has done exactly that in his books, The Art of Computer Programming. Maybe some of you know the book. Many know the book, but haven't ever read parts of it. He does exactly that. He goes for all algorithms down to a level of the RAM and counts all the instructions precisely. It's doable, but it's painful. So most people abstract a bit from that and count dominant operations. So specific points in the program that will be proportional to the total cost if we count those. Here's a few things that we allow ourselves in the pseudocode. Instead of just doing conditional branches, we allow ourselves the usual kind of loop constructions that you would have in Python and other languages. We use variable names instead of registers with numbers. Maybe that's obvious, but yeah, if you work with assembly, you'll have to deal with that. And we'll also make another assumption that I'll talk about in a second. Again, my point about presenting this detailed model is twofold. One is I want to assure you that there is a level of detail that you can go down to if needed. And also, sometimes answering a question, for example, about sorting, we'll come back to that, requires that you specify what model you're working on. Even if your programs are abstract pseudocode, saying how fast an algorithm is might need to tell details about the model. So it's kind of something that's looming in the back, and we don't always go down all that level, but it's important to know how to resolve this. One last assumption that we use in our pseudocode, which is a bit of a bigger thing. It's again, if you've done an undergrad in computer science, maybe you've done a lecture on operating systems, and then again, you would know in detail how this works. Otherwise, take my word for it that it's a solved problem, but we'll just assume that this is already somehow done. If we're working on a RAM like I defined it, there's no such thing as structured memory. Memory is just this one giant array, and you can use as much of it as you want. We assume it's as long as you need it, but there's no structure to it. And it's super painful to write programs that way.
RAM architect doesn't deal with space complexity.
Sorry, say it again. The RAM
architect doesn't deal with space complexity.
Right, so the question is about the RAM model and space complexity. If you want to define the used space, you would take the furthest you access the memory. So you would assume you don't use, or there's the memory that you don't ever touch doesn't need to exist.
Let's say I have designed one algorithm. Let's say Fibonacci series, one with recursion and other with memoization. Now I have two systems. One follows the standard system prediction computer, and another one follows this RAM architecture. And the recursion approach I have put it in the RAM architect, and the memoization algorithm I have put in 64 bits. So is there any point where efficient algorithm will cross the RAM architect algorithm? That is recursion upgrade and memoization to
All right, so the question was about comparing different maybe I will have to take it offline and I have to ask you about the details. What we'll assume is that all algorithms are operating on the RAM. And I guess they all run on the same RAM with the same W. That can have consequences for the algorithms. Oh, the input, okay, I didn't talk about the details about the input. So the standard assumption is the input is initially written in the first n cells of the memory. And you can read and overwrite that. And at the end, you'll leave the output in the first few cells of memory. But you can change these conventions. That's not too essential. But yeah, you're right. I mean, there's already a full slide. There's some details that I left out. I tried to leave out those where no matter how you fill them, it doesn't change the model substantially. But yeah, maybe have a look at the book. They're a bit more rigorous about that part. Because you brought up recursion, recursive algorithms is another useful programming technique. Doesn't exist on what I defined on the RAM, right? Doesn't have any system stacks. It knows nothing about that. That's all something we'll assume that it exists without worrying too much about how it's done. So we'll assume that we have some sort of memory management built in. So we're able to just say, give me a free piece of memory of that size. That's similar to what you can do in C. Or you can allocate an array of a certain size with a certain type of objects. We'll also assume that you can allocate objects from some object-oriented program. If you have a class and you instantiate that, similar to what Python offers, we'll assume that that's also handled by this operating system that's running on this RAM without us touching it. If I talk about pointers in algorithms, that's basically just a number. It's an address of some memory cell. And that's what it is in reality too. But memory safe languages, I don't know if Python is memory safe with all the C extensions, probably not. But Java is a memory safe language that guarantees to you if you have a pointer, you're never gonna access a piece of memory that wasn't properly allocated. You don't get this buffer overflows in that sense, at least. So that sometimes they talk about references to make the distinction to a pointer that could be an arbitrary number in memory. For the algorithms, we won't make that distinction. A pointer and a reference is the same, and it's just a number of the address in memory. And yeah, as I said, recursive calls, all operating systems have a system stack where you can call functions recursively and so on, or non-recursively. We'll also assume that exists. Okay? That's a bit of a slide for everyone who's seen some of this before. If not everything on that slide makes too much sense for you, don't worry too much. I just wanted to put this up so that those people who know about it know our assumptions on it.